Sente? Ok, buongiorno a tutti, grazie di essere intervenuti. È un mio grande piacere introdurre Alberto Bessan della Penn State University, dove è titolare della Eberly Family Chair dal 2008, mi sembra. Non avrebbe bisogno di presentazioni, però comunque dico due cose. Un famoso matematico ha ottenuto risultati molto importanti in numerosi e svariati campi dell'analisi. Solo per citarne alcune, i sistemi iperbolici di legge di conservazione, l'equazione di Jacobi, la teoria del controllo, giochi differenziali. Inoltre ha ottenuto anche vari premi, tra cui il Booker Memorial Prize nel 2008, il primo SIAM per l'analisi delle equazioni differenziali e derivate parziali, e poi il premio Feltrinelli qui in Italia nel 2006 dato dall'Accademia Nazionale dei Lincei. E infine volevo citare che è stato plenary speaker al Congresso Internazionale dei Matematici nel 2002 a Pechino. Comunque mi fermo qua con le presentazioni perché tutti noi lo conosciamo molto bene e oggi parlerà di optimal control of propagation, fronts and moving sets. Quindi lascio la parola ad Alberto.
Okay, well, thanks a lot for the introduction, for the invitation, and thanks to all of you for coming. So this talk, I will talk about two different type of optimization problems. One on control of propagation fronts, the other on moving sets. And they both come as approximation of one single type of problems. And to explain the original motivation, it comes from a control problem for a reaction-diffusion equation. So think of UD is the population density. Okay, let's see. Okay, perfect. So think this as a population density of, let's say, an invasive species, let's say mosquitoes, or just to have something to think about. And the control alpha is the control effort. So what we want to do is eliminate as much as possible of these species. So we have a reaction diffusion equation here, where f of u typically, I think, has a graph of this form. So it's normalized to 1, so that the maximum population is 1 at carrying capacity of the land. And then we can add some control, and with this control, let's say spraying pesticides, for example, we can reduce this population. So what we want to do is to reduce it to a simpler problem. That is, so here we assume that we have two steady state. So u is equal 0, so the free state, no mosquitoes, and another u is equal 1, a contaminated state. And these are both equilibrium states. So we expect that in general, a solution will consist of two regions, one where the solution is almost 1, another where it's almost 0, and these will be separated by a rather thin interface. Okay. So instead of controlling all parabolic equations, so a function which can take any value between 0 and 1, we want to control the motion of a set. And this is the set where the function is almost equal to 1. Okay. So we are approximating a general function with a piecewise constant function that can be either 1 or 0. So omega t is the set where it's almost equal to. Okay. And then this leads to a problem of moving a set in an optimum. Okay. So how do we control a moving set? Well, first, we can describe the motion by assigning the inward normal speed, c of x, at every boundary point. If I say at which rate I am shrinking the set at the point x at every boundary point, of course, this describes the motion of the set. Okay. But Now, to do this, I need also to introduce a cost for this control. And for this, I need to introduce a function E of C that depends, of course, the fastest I want to shrink this set, the more I have to pay for the cost. So think of how many pesticides do I need to do to eliminate the insects from a certain region. Okay. So at time t, the total effort, which is essentially the cost of the control, will depend on the inner normal speed at every point on the boundary. And that is the type of cost function that I will consider. Okay. So the faster you want to shrink, this E will be an increasing function, so the more you pay, roughly speaking. Okay. So now the point is, how do I come up with this function E of C? Of course, this is, I can come up with any function I like. Of course, any increasing function would lead to a meaningful optimization problem. But I want this function to be related to the original parabolic equation. Okay? And so this leads to an auxiliary variational problem to determine this effort E of C, this scalar function E of C. And the idea is this. See, if I put the control is equal to 0, so the negative term G is not there, okay? And this leads to a traveling wave because F pushes it up, right? So I would have a traveling wave to the left because this contaminated area will increase, okay? This is classic result you can find, for example, in Five's book on reaction-diffusion equations. And with that particular function F, there is one and only one speed C star, which in this case is negative, that describes a traveling wave between 0 and 1. That would be the speed of an uncontrolled trunk profile. On the other hand, if I add this negative term G of alpha and U, which I can think simply as alpha times U is the standard choice here. Well, in this case, I'm pushing it down. So it's quite possible that if this term is negative and large enough, I can produce a traveling wave which actually travels to the right. That means I'm shrinking the contaminated set in this case, right? So in this case, the control traveling from profile can move with any speed C greater or equal than C star, depending on how big this control function is in general. That's what we would expect, okay? So now the question is, how do you put an optimal control to achieve this traveling speed? So the type of optimization problem I want to consider for a traveling from is this. I assign a speed C bigger than C star. If C is C star, then I put zero control works, right? If I ask for the speed to be bigger than this, among all positive control functions which yield a traveling profile with this particular speed, I want to find one with minimum L1. So I want to achieve a traveling wave profile with minimum F. Okay, how do I get this? So more precisely, formalizing this problem is minimize the integral of A of alpha among all possible non-negative functions such that there exists a traveling wave profile. So that is a solution to this second order ODE, and here C is the speed of the traveling profile, that at minus infinity is 0, at plus infinity is 1. Okay. So how do we find this optimal control? Well, here would be the picture, for example. Well, everyone knows that you can transform a second order ODE into a system of first order ODE, right? So that's the second order ODE. You can transform this into a first order system, and a traveling profile corresponds to a path that starts from here and ends up at here, 0, 0, and here would be 1, 0. Okay, so I need to find a solution of this for some control alpha that starts from here and goes here. Now, if C is bigger than this C star, which is the speed with 0 control, well, of course, there is no such solution because this would be the unstable manifold through the origin for the equation where alpha is 0. Okay, just for the ODE. And this would be the stable manifold through this form. And of course, these two manifolds don't match, so there is no such solution. However, if I am allowed to put some control there, then of course there are a lot of other ways to go from here to here with a positive alpha. So I have lots and lots of different controls that give me a possible traveling profile. So the goal is, how do I find one which has minimum norm? Okay. Well, usually one looks at this problem as optimal control problem. So what you do, you first prove existence of solution, then you derive necessary condition by subtracting maximum principle or Euler-Lagrange equation, so on. Then try to solve the Contragin necessary condition and determine, oops, sorry, there is something. Okay, and find the optimal solution. In this case, actually, I can show that you can explicitly find the optimal solution right away. And the idea actually is something I learned from one of my professors in Boulder, Colorado, named Harry Perms. The technique is based on Stokes' theorem. So the underlying idea is that you want to write this cost function, which is just the integral of alpha, as a line integral. So first of all, you express alpha using this second equation here. So alpha is this thing here. And now, since du is p of dx, I can write this as a line integral. So for each one of these curves, I integrate this object here along the curve gamma, and that is the cost. Okay. And the beauty of this, as shown in this old paper by Herms and Haynes back to 63, you can see very first issue of Siam Journal of Control. And the idea is that if you define V as this type of V here, so the cost would be just the line integral of V along whatever path you have. Okay. And now I want to compare the integral of any two paths over here, and I can do it immediately by using Stokes' theorem. Okay. So I claim, so first I divide the plane in two parts. One is where the curl of this special field is positive here, and another where the curl is negative, which is this part here. Okay. And I want to say that this line here, that, well, this would be the unstable manifold, then I go on the boundary, and then I go down with the stable manifold, is the one and only optimal solution right away, because I can directly compare this with any other admissible path. And the idea is that if I have another admissible path, let's say this blue one, like that, how do I compare the difference between the integral V in gamma 1, the red, minus the integral over gamma 2? Well, this is the integral over of the curl in the region enclosed by these two curves. But of course, I have to split these regions because there is one which is counterclockwise, that's a plus sign, and another clockwise, that's the minus sign, right? And if I choose this particular curve here, then it's clear that this part, I am integrating omega in this region where omega is negative. So this gives a negative part. And then I'm integrating minus omega on omega plus, which is this part here, where it comes with a minus sign because omega is, well, omega is positive here, but comes with a minus sign. So the whole thing is negative. Okay. So this is an example where we can explicitly determine this the optimal control. And now one can also compute the cost as a function of the wave speed. Okay, and it has a graph like this roughly. So of course, if you take no control at all, the speed would be c star negative. That means you are moving to the left. If you want to move to the right with bigger and bigger speed, as expected, it means that you have to spend more and more effort, let's say, in pesticides, and therefore you have the cost, which is roughly with linear growth. In fact, you can explicitly find the asymptotic shape of it, okay, provided that f has this particular shape, which is quite reasonable as describing the growth of a population. Okay, here I've added just a few slides saying that you can play the same game with any other reaction diffusion equation. In the previous case, we had a scalar equation describing just one single population. But you could have a system of many equations describing different populations. For example, this is kind of inspired by the Xylella epidemic. So you have U is, as before, the density of insects, I times U. So I is the infection rate. That would be the density of infected insects. Then theta would be the fraction of infected trees. And alpha again is the control, how many insects will kill. So these are negative terms. That means how many insects will move. And then there are these two terms that say that the trees infect the insect and the insects infect the trees. So what type of results one can get for that type of system? And this was done with one of my last PhD student in Penn State. She just graduated a month ago. So in this case, what one can prove is that for every speed c between c star and 0, you can find an optimal control that achieves a traveling wave with speed c, like this. So in this case, we are assuming that on one side, this region asymptotically is free of insects. No insects on this side. And on this side is full of insects at carrying capacity, so almost 1. Okay. And in this case, by removing some insects, we can slow down the propagation of this traveling wave, but up to 0. And well, here's the idea that trees never recover. So you can slow down the propagation, but you cannot go back, push it backwards, even killing insects. Okay. Another thing which I think it was curious, at least not expected, is that what happens if instead you start with a density of insects which is 1, both at plus infinity and at minus infinity, but here the fraction of infected insects is 0 on this side and very high on this side. So this is another type of traveling wave still joining steady states at plus infinity and minus infinity. And here, the difference is in that red one, the number. So when you x at axis minus infinity, you still have a lot of insects. Okay. Can we slow down the propagation of the infection in this setting? So can we achieve a slower traveling wave? Surprisingly, it's not the case, because actually what we thought is that if we remove insects in the middle here near the interface, right, then we kind of create a buffer between healthy insects and sick insects. And by doing so, we should at least slow down the infection and achieve a traveling wave with slower speed. But it turns out that this is not possible. So this is because the traveling wave essentially is determined by the asymptotic, the linearization at infinity. So there is some obstruction in doing this. So no way of slowing down the if insects are all over the place. Okay, now this is first part of the talk, right? This so far I talked about optimization problem for traveling fronts. What does this have to do with the original problem? And then I shall discuss optimization problem for moving sets. Okay. So let's look at one particular optimization problem for that parabolic equation. For example, I would like to reduce the size of the population over time, plus this would be the terminal size of the population. And then I have a cost of the control that depends on how much effort I take. Okay. So that's a natural thing, functional I would like to minimize. Okay. On the other hand, I could consider a similar optimization problem, but for a moving set. So for a moving set, I'm thinking that the population, the density is either 0 or 1. Okay. So here, again, I have the control cost, then the contaminated area over time, plus the final contaminated area, which is pretty much the same as before if I think as the density is either 1 on omega and 0 outside omega, right? And here, that's the key. The total control effort at time t is the integral over the boundary of my set at time t of this effort. And this effort is not an arbitrary function I cook up just randomly. This is the minimum cost of that variational problem I discussed before. So for every speed beta, I can look at the traveling front with that speed, and then the minimum cost of the control that achieves a traveling front with that particular speed. Okay. So for example, let's see, this might be the value, the set at time t. And let's say I want to put some effort here and shrink the set on this side. And maybe I don't put any control here. So over here, the set expands. Okay. So the cost of the control would be this integral here, or the effort, which is the integral of the effort depending on the normal speed. Okay. And this is the one theorem that ties the two things. So, well, intuitively, what we would like to do is to recover the optimization problem for a moving set kind as a gamma limit of the optimization problem for the parabolic equation. Okay, this is the eventual goal. It's still an open problem, quite difficult open problem that we did not solve. In fact, what we can prove is the following. So let's rescale the independent variable like t epsilon t x goes into epsilon x. If you do this rescaling, well, this is like taking a picture of the land from very far apart. So you see a very thin interface. If you take like a picture from the satellite of what is going on, right? So from the original equation, after you do this scaling, you get this type of equation here. And then you can, again, study optimal control for this one. And so we want to say that the cost for moving a set can be achieved also as a cost for controlling this. So more precisely, let's say I start with a moving set, which is smooth. That means the set has at least C1 boundary, okay? No corners here, okay? And let's say that I have an inward normal speed, beta is beta of Tx. So at each point on the boundary at each time, I prescribe the normal speed, okay? Then I can find a family of control function alpha epsilon, which I plug this in the parabolic equation. Okay, so I can find control function that I plug in here in such a way that if I look at the solution u epsilon of the parabolic equation, what I have is the following. Well, first of all, as epsilon goes to 0, the L1 distance between the solution of the parabolic equation and the characteristic function of this set goes to 0. Okay, so it means the solution of the parabolic equation, in fact, is 1 or 0 and very thin interface. Okay. And then the total, the L1 norm of the control is converges to this effort function. That is the particular effort function which is describes the minimum cost of pushing of this achieving these traveling rates. Okay. So if you have seen anything about gamma convergence, you know that to prove gamma convergence, you have to establish two things. One is easy and one is hard. Okay, this is the easy one. Okay. The hard thing would be to say that you cannot do any better than this. So here we start with control through the moving set, and we can say we can achieve this same cost with a control here for the parabolic equation. The other thing which is more difficult is saying that no matter how we use this control, we cannot do any better than this cost of the control for the moves. Okay. Okay, so this, now we come to the second part of the talk, and this is control problem for moving sets. Okay. There are many control problems you can think about. So here is the basic one is this optimization problem. So given an initial set, think this as the contaminated set, we want to shrink it to possibly a point, to the empty set as fast as possible. But so we want to find a motion that minimizes this cost function. So the integral of the area over time plus the terminal area, and then a cost of the control, like that. And again, the total control effort, depending on the inward pointing normal velocity, is given by this. And then here we take a function of the total control effort. A reasonable thing is to take s squared over 2. So, or we could take a function which is 0 if s is less than m, and plus infinity if s is bigger than m. So in this case, instead of a cost, it would be a constraint. this is equivalent to say that the total effort at any given time should be less or equal than m. So in this case, it's not a real cost, but it's just a constraint for each time t. So the result we have are existence of optimal solution, some necessary condition for optimality, and this has been, it just appeared on Journal Differential Equation. This is with two postdocs, Maria Teresa Chiri and Najma Soleil. They were both postdoc 1 year ago. Now they are assistant professors. Okay, so let me just describe briefly how do we get necessary condition for optimality of a moving set. Okay. It's in the spirit of the classical Pontryagin maximum principle. Right? In the classical Pontryagin maximum principle, what you do is a needle variation. So you start with a reference trajectory. Let's say this is a reference trajectory, possibly the optimal one. And then what we do in a neighborhood of time t, we make a big change in the control. So instead of being here, we are here. And then we let the control to be the same as before from t to the terminal time. And then we want to understand by how much the cost is increased or decreased by this needle variation. And to keep track of this, we need a dual vector, which economists call shadow prices, right? And this would be the price that you would be willing to pay in order to move the state to some other point. Okay. So if you move the state from here to here, the change in the cost would be the inner product of this times the vector p. So that allows you to keep track of what you gain or what you lose by a small perturbation at time t. And then you can decide if this is a good perturbation that lowers the cost or if it's not. Okay. And it's a very similar thing you can do for these moving sets. So what we do is parameterize the set. So actually, we parameterize the boundary of the set. So the boundary at a fixed time t is parameterized as psi x of tau c. Let's say these could be sets at different times. Okay? And then for every psi, the curve tx of t psi, we choose them so that it's always perpendicular to the boundary. Okay. We can, well, assuming some regularity, we certainly can do that. Okay, so this is a picture of kind of a needle perturbation of these moving sets. So let's say this is the original set. Think of this as the contaminated set at time 0. And then we are shrinking this. At time tau might be this one. At the terminal time, it might be just that. Okay. And now I choose one particular point, tau psi, tau theta, this one. And I make a perturbation here. So let's say I increase my control. So I clean up a small area near this point here. And then after that, I keep my control effort exactly as before. So I just increase my control effort here. And then, of course, if I make this change here, at a later time t, of course, the set, contaminated set, will also be a little bit smaller, and the terminal time also will be a bit smaller. Okay, so at time tau, small region is here from the contamination, and if the control effort remains the same at all the other points, then these sets omega t are replaced by slightly smaller sets omega epsilon, and I reparameterize these boundaries by exceptional type c. And then I need a dual variable. What is the meaning of this dual variable here? Well, the dual variable would be y of tau theta, and this accounts for the reduction in the total cost, I can think this as the value of the cleaning service per unit area. So if I can pay for somebody cleans up a unit area at that point, how much should I pay? How much my total cost decreases if I can clean up just at that point? And this is what I call this Y of tau zeta. Okay, and then, okay, I don't want to get into big formulas, very complicated. So let me discuss just the simplest case where instead of the cost of the control, I have just a constraint. So the total effort has to be less or equal than m. This kind of simplifies the result. Okay, and the total effort, let's take the maximum between 0 and 1 plus theta. So it would be something like 0 and piecewise affine cost. Okay, so that means that with no control, my set expands with unit speed in all directions. And implementing a control along the boundary, I can clean up a region of area m per unit time. This is the rules of the game if you add this constraint. I'll repeat this over and over in the next slides. But so what it means, so that the area of the set omega t increases along depending on the perimeter because it expands in all directions along the perimeter, and then I clean up this a set of area m per unit time, right? So d by dt of the area is the perimeter minus m. So this is the basic setting. And these are the necessary conditions. So this is the equation that describes how this dual variable changes in time along these orthogonal trajectories. As you can see, in this case, it's particularly nice because it depends only, it's a linear equation. Of course, the dual variable always satisfies a linear equation. But here depends only on the curvature of the boundary. Okay, so if the boundary has positive curvature, it increases. If negative curvature, it decreases. Okay. And then there exists a Lagrange multiplier, lambda of t, which, of course, you can expect the Lagrange multiplier because I have this constraint, right? That the total effort is less or equal than m. And such that this thing here is equal to the minimum value over all beta. And this is for every t and every xi. Okay, so okay, this would be kind of the control effort, how much you spend in the control, and this is how much you gain by shrinking your set. Okay, and this is in a way optimal. I realize this would not say much to you, but so I rewrite this as in a way which is more easily understood. So from this equation here, you get more concretely this equation here, this condition. So at each time t, the boundary of your set is the union of arcs where the control is active. So in some part of the boundary, you are actually pushing inward. In other parts, you're not doing anything, and the other parts of it's expanding with speed 1. Along the active arcs, all of these are circumferences, arc of circumference, all with the same radius r of t, and these active arcs join the other tangential. This is main result. And in particular, in that paper with the two postdocs with Maria Teresa Iri and Najme Saleh, one conjecture we had is that if you start with any convex set, what is the optimal strategy to shrink it to a point, let's say? Well, you see, the rate at which the area decreases is the length minus m. So what you want to do is to decrease the perimeter as quickly as possible. Okay. So at any time, you want to put the control on the portion of the boundary where it will be most useful, most productive to reduce the perimeter. And that is precisely where the curvature is maximum, right? So for example, if you start with an ellipse, what are you going to do? The optimal strategy would be to have an arc of circumference here, an arc of circumference here, while these parts where the curvature is very small, you let them expand. Okay. And here the same. You start putting the control on the four vertices, and so this part will expand, and along the vertices it will contract. Okay. So this is one of those theorems that you think it's kind of obvious, and then you try to prove them mathematically rigorous. And well, first seems that we could do it in 10 pages, but then Bianchini slipped in one sentence. It's easy to see that the set has to remain convex. And that's easy to see. It means 30 more pages of proof, but now it's complete. It should appear, I guess, in a month or so, at least the preprint. I don't know how much time I still have. Now, maybe the last topic I wanted to discuss is these problems with geographical constraints. So what I want to do here is eliminate contamination, but on an island. Okay. So instead of working on the whole plate, now I have an island, and initially, let's say that it's completely full of insects, and I want to remove them, let's say, as quickly as possible. So this would be a constraint, null controllability problem. The first thing is, given M positive, I want to find a strategy such that initially the contaminated set is the whole island, and after some time, it's empty. Okay. So for example, something like this. Initially, it's all shaded, and then I had clean up more and more until at the end it's all cleaned up. Okay. And here the constraints is just as before, that I can clean up an area of M per unit time, and the contamination keeps expanding with speed 1 in all directions. Okay. Now you can see that, can I make progress in here? Well, if the length of this interface is less than M, of course I can make progress. But if it's more than M, it will come back. Right? So now the question is, for which values of M can I actually eradicate this contamination? Okay? And this is related to two geometric invariants of this island, of this set. So let me describe in detail these two geometric invariants. So the first is, as shown in here, this is big K of V. So this is a minimax. So what I want to do here, well, forget about the exact definition, but what I want to do is slice this set in such a way that the maximum length of all these slices is as short as possible. Okay. For example, if I have this equilateral triangle, what is the best way of slicing it? Well, I mean, the longest slice always has to go through the vertex C. Okay, so in this case, K of V would be the height. Okay, there must always be one slice which is at least as long as the height. If I'm not careful, it could be even worse. On the other hand, there is another type of invariance, which is the following. So let's say K of B lambda. For every lambda, I look at a subset whose area is lambda times the whole area of the whole set. Okay. And now I want to minimize the perimeter. So for example, here. So I want to minimize the length of the boundary, but of course, not the whole boundary, just this boundary inside the island, right? For any given lambda, and then I take the maximum over all possible lambda. Okay, so this would be a max min. Okay, it turns out that this is different from the other one. For example, in this, you see, let's say again the equilateral triangle. If I take a set whose area is 1/2 or the area of the whole triangle, and I want to have this boundary of this set as short as possible, what should I take? Well, as long as the measure of this set is less or equal than 1/2, I should take a set like this. When it's bigger or equal than 1/2, I should take a set like this, like that part. Okay. So in this case, the maximum would be the length of this arc of circumference. Okay. When the first case, when I slice continuously, I have that would be the height. Okay. And it's clear that this one is strictly less than the height. In fact, the height, well, you know, it's 0.866, and this one would be 0.643. Okay. So again, the rules are always the same. The contaminated set expands with unit speed in all directions. And by implementing a control, we can clear an area m per unit time. So that is the ODE that describes how the area changes in time. Okay, so the theorem says that if m is if the null controllability problem has a solution, then m has to be at least as big as the smallest of these two invariants. So if it's smaller than the smallest one, there is no chance you can clean it up. And this second says that if m is strictly bigger than the biggest one of these two invariants, then for sure you can clean up yourself. Yeah. Okay, so this is a feasibility condition. Tells you if you can clean up or not. But now, what is the optimal strategy to do that? And well, this is still largely not understood, I must say. So again, initially the whole set is contaminated, and we want to, let's say, clean up the minimum time. Okay. Again, we have the necessary conditions for optimality, which are described here. So at each time, the interface between clean and contaminated is the union of arcs. The blue arcs where the control is not active. So here the contaminated region expands. And this part, in contrast, this is where we put the control. And these are always arc of circumference. So active arcs are circumferences, all with the same radius, which is just a function of time. Active arcs join the other ones tangentially, and they meet the boundary of the island perpendicular. So this is perpendicular. Okay. So these are all necessary conditions. Okay. We have also some sufficient conditions, which sometimes they apply, but in very few cases. So the idea is this: assume that I can slice my set, which in this case is an ellipse, with sets, all of which satisfy the classical DDoS problem, in the sense that all of these sets, of these slices, minimize the perimeter for a fixed area, right? DDoS problem is, well, given an arc, a rope, let's say, with a fixed length, you want to enclose the maximum area. Here, I'm doing pretty much the same thing. For a fixed area, I want to minimize the perimeter. Okay? So let's say I can slice my set in with curves, and such that the boundary, the one-dimensional measure of the boundary, is the minimum among the boundary of all sets which have the same area. So that means that every time t, I'm solving a DDoS problem. If I can do this continuously in time, then this is an optimal. So yeah, I like to think of this type of problem as time-dependent DDoS problems, right? Because the ideal thing that you would like to do is having, for each fixed time, solving the DDoS problem, minimizing the interface, the length of the boundary for a fixed area. And this area keeps shrinking. However, this is not always easy to implement. In fact, in most cases, the previous theorem does not apply. Let's say I want to clean up this triangle. Well, of course, initially it's fairly clear. I can start cleaning up in a neighborhood of this point, and then I will clean up a region which is just a sector. This is an arc of circumference perpendicular here and here. Okay, but at some point I cannot go all the time. So this is how my optimal strategy will start, and then I know also how it should end, because as the terminal time approaches, I will have cleaned up everything except a sector here, and then I clean up. But how do I pass from here to here? That's the question. And in this case, we can guess, in fact, we can explicitly compute at least a strategy that satisfies all the necessary conditions for optimality. We cannot prove this is optimal, but I'm pretty sure it is. So the idea is that at some point, you have to pass from this to this one. Okay? And you do it by inserting an interface, a free interface, where the control is not active. So at some point, all the control is active here, and therefore this moves back. So the contamination first, it decreases, but then it comes back, and then it increases again. Okay. And let me see if I can show you a little movie. This was done by Maria Lang, who is my daughter. One afternoon, she had nothing else to do. Okay, so this is the initial triangle is completely contaminated. And now let me show how it should be. Let's see. Okay, so let's see. And at some point, there is this interface, which is straight, and it goes from one to the other. So the most interesting part is, let's see, in the middle. So it has to pass from here to here. So here you can see this is an interface where the control is not active. So here, this is moving back. And all the control is concentrated on this small arc of circumference until it passes beyond the upper vertices, and then it cleans up again. Let's see, it goes over and then it cleans up the other. Okay, so I think about to conclude. I've not much to. Let's see, full screen. Yeah. So I don't have much more to say, just a few open questions, things that we still are struggling to understand. For example, for an isosceles triangle, at some point, it has to break the symmetry because either we have this one and this one, right? How does it break the symmetry? Or if you have an arbitrary triangle, which is not symmetric, not isosceles triangle, what is the interface when the free interface when this reaches this point here, right? The equation for that interface is still a mystery. We are working on that with Elsa. In another thing that we would like to understand, at least what is the generic structure of the optimal strategy? In general, for something like this, think of as a triangle with smoothed out corners, right? What is the optimal strategy? Well, initially it should start with arcs of circles, but someplace it has to go back because you cannot just jump from an arc like this to an arc like this, right? It would go back. So initially it's easy to understand how it goes because you take a point where the curvature is maximum, and then here you can fit a family of circumference which are perpendicular here. This you can do if and only if the curvature has a local max or a local mean. But then at some point you hit this place where the curvature is very large, and then there must be some free interface, and this would go back, and then you have to match these circumferences to the free interface. And the key thing is to understand an equation that gives you the maximal size of this free interface, which still is not much understood. So it seems rather elementary problems, but if you look at the details, it comes out quite singular ODEs describing, for example, an interface like this. So it is tricky. Okay, I think I can stop here. Thanks for the attention.
Yeah. So when you explain the problem of treating the ion,
yeah,
your strategy was to have the ion completely clean at time big T.
Yeah, well, one problem is, can you make it or not? Exactly.
This is the problem. So
yeah.
My question is, this big T comes into the picture somehow or not? Because it seems, I mean, it would be somehow reasonable to think that the larger is big T, the easier is to find a strategy.
No, the first theorem says that either you can or you cannot.
For every T.
Yes, no way. No,
a very small T.
Oh, no, this is for sufficiently large T. Yes, no, of course, you shrink your, the area is shrank by M. Okay, so at worst, well, the best you can do is reduce the area by M. So there is a minimum time for sure because you take the total area divided by M.
I mean, the constraint of big T, which is not written in the.
No, here big T is
Not
arbitrary. Is arbitrary. Yes, sufficiently large.
Arbitrary, but sufficiently large.
Well, yeah. I mean, I can tell you right away that T must be at least as big as the area of the whole thing divided by M. That for sure. But well, in general, the fact is, for example, here, if the diameter, if the shortest distance from here to here is bigger than M, then you'll never go beyond that because it will come back, right? So there are conditions, and these are given by these geometric invariants. So in fact, we know that there is a minimum M for the triangle that we can explicitly compute, and this is some number between these two. In fact, it's close to 7. It's slightly less than 7. You can make it. Yeah. So this is a general result. Oh, yeah, well, we problem is that we still do not understand triangle. Okay, so this is one. If we can understand triangle, we would go up to quadrilaterals. I think we can. There is a chance of doing this. We can understand this, and then actually, what I think is interesting is find describe this optimal strategy for generic convex sets. Generic convex sets are, let's say, sets which are smooth, or at least C2, and where the curvature has a finite number of local mass, local mean. This is very reasonable. And here, probably corresponding to a local mean, you would have a free interface which is as large as possible. If I can understand this one, then I know the interface at all nearby times, because this evolves by, I mean, the distance between these two depends on, it's just the time. Okay, so if you know the interface at the time for its longest, then you know the interface at all the other times. So, but the point is, what kind of ODE describes this one? Okay, which is not so obvious. We are working on that with Bessan.